Welcome viewers. In this video, we'll see the magnetic field intensity due to circular current loop, followed by the two problems. Now we'll refer the diagram. One lengthy wire is available. That wire is two ends are joined together and the circular loop is formed. One lengthy wire will be available. That lengthy wire, two ends are connected together and form the circular loop. So the radius of the circular loop is a meters. Our aim is to find the magnetic field intensity at this point P, which is at a distance h meter from the center of the current loop. This current loop is assumed to be having several current elements, n number of current elements available. We consider one current element at this point, ideal vector. The distance between this current element and point P is r meter. The h is the magnetic field intensity. dH is magnetic field intensity due to ideal. There are n number of ideal available. We consider only one ideal, so that there is magnetic field intensity also small, dH. By integrating this dH, we will get total magnetic field intensity. Right, one lengthy wire available. The two ends of the wire is connected, so that form the circular current loop. The radius A. Our aim is to find the magnetic field intensity at point P, which is at a height of h meter. There are n number of current elements available. In that, we consider one current element at this point. The distance between this point and point P is r meter. The angle between this r and ideal vector is 90 degree. From the diagram, it is clear. So this dH is the magnetic field intensity due to this small element, ideal. So this triangle is drawn separately. This angle alpha, height A and R. So from that we can find the sin alpha. Sin alpha is opposite side by hypotenuse, A divided by R. It can be used in the derivation. Right? Sin alpha equal to opposite side by hypotenuse, A divided by R. We'll see the description. So it is required to determine magnetic field intensity at point P, which is at a height of h meter from the center of the current loop. Right? The point P is located at a height of h meter from the center of the current loop. At that, we are going to find the magnetic field intensity. How the circular current loop is formed? The circular current loop is formed by wire bent in the form of a circle. The wire is bent, two ends are connected together and the circle is formed. The loop is assumed to be formed by several current elements. There are n number of current elements available in the entire loop. In that, we consider a current element ideal. The distance between this current element point P is r meter. Then this dH vector is the perpendicular to the plane containing vector ideal and r. In the diagram, it is clearly shown. The angle between ideal and r is 90 degree. Now we'll go to the derivation. The normal component of magnetic field intensity is given by, because due to this wire we have only normal component. There is no horizontal, there is no vertical component, only normal component. So dH equal to dH cos 90 minus alpha. Normal component is, it is multiplied by cos of theta. Cos 90 minus alpha can be written as sin alpha. What is dH? From Biot-Savart's law, the standard form is available. Ideal vector cross r vector divided by 4 pi r cube into sin theta, sin alpha. So this is written from the Biot-Savart's law. What is a vector cross b vector? AB sin theta. So ideal r into sin theta. The angle between DL and R is 90 degree. So it is 90 degree. So ideal cross r vector is ideal r sin 90 into sin alpha divided by 4 pi r cube. Now here r is there, here r cube is available. So here one this sin alpha, is replaced by A by R. From the triangle we calculated sin alpha equal to A by R. So this R got cancelled. Sin 90 is 1. So finally what we have? I into A into dl, IA dl divided by 4 pi R cube. IA dl divided by 4 pi R cube. So this is due to only small current element. This dH is the magnetic field intensity due to small current element. So by integrating on both the sides, we'll get the total magnetic field intensity. So integral dH equal to integral IA dl divided by 4 pi R cube. IA divided by 4 pi R cube is constant. Only we have integral dl. What is integral dl? Integral dl is L. L is nothing but 2 pi A. That is, one lengthy wire is available, length L. This wire is formed as a circle, as a current loop. So this radius is A. So the length of this wire is equal to circumference of this current loop. Both are equal. What is the circumference? 2 pi A. That is given. Length of this wire, because this wire only formed a circle. So the length is nothing but circumference. Both are equal. L equal to circumference. Circumference is 2 pi A. Right? So integral dl is L. L is nothing but 2 pi A. Here 4 pi is there. Here 2 pi is there. Got cancelled. 2 is there. So I into A square. I into A square divided by 2 R cube. IA square divided by 2 R cube. We got the value. We take it as equation number 1. H equal to IA square divided by 2 R cube. Now we'll see the other forms. So from the triangle we can write R equal to, using Pythagoras theorem, A square square root of A square plus H square. So from this triangle it is given R square equal to A square plus H square. So R equal to square root of A square plus H square. That is written. So R equal to, it can be written as A square plus H square whole power 1 by 2. Square root is written as 1 by 2. But in equation what we have? R cube. R cube is needed. IA square divided by 2 R cube. R cube means you multiply with 3. Already 1 by 2 is there. So 3 into 1 by 2 is 3 by 2. R cube equal to A square plus H square whole power 3 by 2. Right? So R equal to square root of A square plus H square. That can be written as A square plus H square whole power 1 by 2. Here 3 is needed. R cube is needed. So A square plus H square 3 into 1 by 2. That is 3 by 2. Now we can substitute this value in the equation number 1. What is equation 1? H equal to IA square divided by 2R cube. Right? So this R cube can be substituted from this. A square plus H square whole power 3 by 2. So what will happen? H equal to IA square divided by 2 into A square plus H square whole power 3 by 2. So this is another form in terms of height. In the equation 1 what we have? A and R. A and R is available. A is the radius of the current loop. R is the distance. Here and in terms of height is available. A and height. So this is another form. Suppose if the center of the current loop, if you consider the point P is located at the center, or what is the magnetic field intensity at the center of the current loop. So at the center of the current loop what will happen? The height is 0. So the height is 0, so that H equal to IA square divided by 2 A square plus H square whole power 3 by 2. This height is become 0. This height become 0. So what will happen? IA square, this A square into 3 by 2. So this 2 got cancelled. We will get A cube, right? So this what is available here is A square whole power 3 by 2. So this 2 got cancelled. What we have? A cube. So IA square divided by 2A cube. Here A square cancel, here 2 terms are cancelled. So what we have? I divided by 2A. This is at the center. At the center of the current loop, the magnetic field intensity is I divided by 2A. Suppose if n number of turns are available, what happen? Ia square divided by r2 r cube into n. You have to multiply with number of turns, right? H equal to Ia square divided by 2r cube into n. That is due to n number of coils. Here we have only one circular current loop. If n number of current loop available, Ia square divided by 2r cube into n. So we have the four different expression available. First is Ia square divided by 2r cube. Then r is substituted in terms of height. That is the second expression. Then height is 0 at the center. That is third expression, this one. This will be fourth expression in terms of number of turns. Now we'll see the problem. We'll see the first problem. What is given? A wire carrying a current of 100 ampere is bent in the form of circle. So this is a circular current loop of diameter 10 centimeter, right? See here, the current is 100 ampere, diameter equal to 10 centimeter means radius equal to 5 centimeter, that is 5 into 10 to the power minus 2 meter. So what is the question? Flux density at the center of the coil. First one, at the center. Flux density at a point form a axis of the coil and 12 centimeter away from it. That is at a height of 12 centimeter. Right? We discussed four different expressions available at the center, in terms of height, all are available. So first one is based on the center of the current loop. Height is 0. Second one based on the height. Height is 12 centimeter. Right? So the current and radius is given. Now we'll go to the first division. Magnetic field intensity at the center of the coil. What is the formula? I divided by 2a. At the center of the coil, height is 0. So only we have I divided by 2a. Already we got the expression. So I is 100 divided by 2 into a. A is nothing but radius. 5 into 10 to the power minus 2. So by simplifying, what we got? 1000 ampere turns per meter. This is the magnetic field intensity. But what we need is flux density. B is needed. So B equal to mu naught mu r into h. There is a relation between mu and h is available. B equal to mu naught mu r h. Mu naught is nothing but constant. 4 pi into 10 to the power minus 7. Mu r is 1. We assume that is a air medium. The height is, the magnetic field intensity is calculated. This 1000. Right? So by simplifying this, what we got? 1.25 into 10 to the power minus 3 Weber per meter square. Magnetic flux density is 1.25 into 10 to the power minus 3 Weber per meter square at the center of the coil. We have one more at the 12 centimeter. When it is the axis is placed at a height of 12 centimeter. That is height equal to 12 centimeter. That is 12 into 10 to the power minus 2 meter. For this, what is the formula? Ia square divided by 2 into a square plus h square whole power 3 by 2. So this expression also we got previously. This is in terms of height, right? So I is 100, a is 5. 5 into 10 to the power minus 2 square divided by 2 into 5 into 10 to the power minus 2 square plus height is nothing but 12 centimeter. 12 into 10 to the power minus 2 square whole power 3 by 2. You have to square this value, add both. For that we need to take 3 by 2. Right? So by simplifying this value, what we got? 57.36 ampere turns per meter. Okay, at the height of 12 centimeter. This is a magnetic field intensity, 57.36 ampere turns per meter. From that we can find magnetic flux density, B equal to mu naught mu r into h. So mu naught is 4 pi into 10 to the power minus 7, mu r is 1, and the magnetic field intensity what we calculated 57.36. So by simplifying this value, what we got? 71.46 into 10 to the power minus 6 Weber per meter square. So this is due to the coil placed at 12 centimeter height, right? So this one due to it is placed at the center of the coil, right? We have two divisions, center of the coil and placed at a 12 centimeter height of 12 centimeter. Now we'll see the next problem. So in the second problem, there are two narrow circular coils available, A and B, right? We'll see the diagram so that it is easier for you. So there are two circular current loops are available. The radius of the first circular current loop is 5 centimeter. Second current loop is 8 centimeter. The center to center distance is 15 centimeter. Right. The current flowing through the first coil is 2 ampere. Coil A is 2 ampere. But the current in the second coil is not given. We need to find. Right. So the radius of first one is 5 centimeter. Current is 2 ampere. Radius of the second coil is 8 centimeter. Current is not known. Center to center distance is 15 centimeter. So what is the other values are given? So the two circular coil A and B and placed at a distance 15 centimeter. Coil A has 10 turns available of radius 5 centimeter and the current is 2 ampere. But coil B has single turn of radius 8 centimeter. What is the condition? If the magnetic field at the center of coil A is to be 0, what current must be passed through coil B? Right? So at the center of the coil A to be 0, in order we need to make it as this coil A is 0 such that what is the current is passing through coil B. So that is the question asked, right? So we'll see the what are the datas. The number of turns available for the coil A is 10, radius 5 centimeter, 5 into 10 to the power minus 2 meter, current is 2 ampere. For coil B, number of turns 1, radius is 8 into 10 to the power minus 2, the IB we need to find. So from the given condition, we can conclude that the magnetic field at the center of coil is 0. When it is 0, it is possible only when the magnetic field intensity due to the coil B, HB, due to the coil B at the center of the coil oppose the HA, which is equal and opposite, right? So magnetic field intensity of coil A, when it becomes 0, the magnetic field intensity due to the coil B oppose the coil A, and it should be equal and opposite. So the magnetic field intensity produced by coil B is opposing coil A and make it as 0. What is the meaning? Both are equal and opposite. HA equal to HB. That is the, from the given condition we got the expression HA equal to HB. So the magnetic field intensity produced by coil B oppose the coil A and make it as 0. Right? So using this condition we can find the current in the second coil. So first we will find the HA. HA equal to NAIA divided by 2A. That is at the center. The coil A we assumed at the center. Coil B we assumed at a height of 15 centimeter. Right? Coil A is a reference. So that it is at the center. NAIA divided by 2A. Normally I by 2A, but here number of turns available, so that NAIA divided by 2A. The number of turns is 10, current is 2 ampere, divided by 2 into the radius is 5 into 10 to the power minus 2. That is 200 ampere turns per meter. So the coil A we assume at the center. Coil B, it is at a height of 15 centimeter, because coil A and B, the distance, center to center distance between coil A and B is 15 centimeters. So that we are using this formula at a height, in terms of height, here at the center. So now we substitute the value NB, the number of turns in the coil B is 1, right? Then IB value is not available. We need to find the IB value. Then B square, 8 into 10 to the power minus 2 the whole square, divided by 2 into 8 into 10 to the power minus 2, the radius of the second coil, plus the height is 12 into 10 to the power minus 2 whole square, whole to the power 3 by 2, right? So by simplifying this, what we got? 0.651 IB, right? So HB equal to 0.651 IB, right? This IB value is not known. Now we have the relation HA equal to HB. What is HA? We calculated 200. What is HB? 0.651 IB. So from that, IB equal to 2 divided by 0.651, that is 307.6 ampere. So the current flowing through the second coil B is 307.6 ampere. So due to this current flow, the magnetic field produced in the coil B will oppose coil A and make it as 0. So in this video, we discuss about the magnetic field intensity due to circular current loop, followed by two different problems. Thank you.